ഹലോ. ഹലോ സാർ. എനിക്ക് എൻ്റെ ഇതിൽ കേൾക്കുന്നില്ല, സൗണ്ട് വരുന്നില്ല. സൂമിൽ വരുന്നില്ല. സാർ സൂം ഉപയോഗിക്കുന്നുണ്ടോ? ഇല്ലായിരിക്കും അല്ലേ? എനിക്ക് ഫോണിലൂടെ കേൾക്കുന്നുള്ളൂ. ഞാൻ ഇതിൽ സൂമിലൂടെ ഓഡിബിൾ ആണോ? അമ്മ ഓഡിബിൾ ടു സൂം? ഇങ്ങോട്ടൊന്നും വരുന്നില്ല സാർ. ഓഡിയോ ഓഡിയോ ഓ സ്പീക്കേഴ്സ് ഒന്നും വരുന്നില്ല. ഹലോ. ആ, സൗണ്ട് ഓഡിബിൾ ആണോ എൻ്റെ? പക്ഷെ എനിക്ക് തിരിച്ചിങ്ങോട്ട് സാർ പറഞ്ഞ ഈ ഫോണിലൂടെ മാത്രമേ കേൾക്കുന്നുള്ളൂ. കുഴപ്പമില്ലല്ലേ? ആ, ഇല്ല, അതുകൊണ്ടല്ലേ. ഓക്കെ ഓക്കെ ഓക്കെ. ഓക്കെ, അപ്പം സ്റ്റാർട്ട് ചെയ്യാമോ? ആ, ഇപ്പോൾ എത്രയായി? 2:26 ആയിട്ടുള്ളൂ. 2:30 അല്ലേ തുടങ്ങണ്ട? ഓക്കെ, ഞാൻ റെഡിയാ. ഞാൻ റെഡിയാണ്. പറഞ്ഞാൽ മതി സ്റ്റാർട്ട് ചെയ്യാൻ എപ്പോഴാന്ന് വെച്ചാൽ. സൂമില് സൗണ്ട് ഓഡിയബിൾ ആണല്ലോ അല്ലേ? ഓ, രണ്ടിലും, യൂട്യൂബിലും. ഓക്കെ. നീ ഫ്ലക്സ് അല്ലേ സ്റ്റാർട്ട് ചെയ്യണ്ടേ? അതല്ലോ അതിന് മുമ്പുള്ളവരെ തീർത്തില്ലേ? സഫസ് പെട്ടെന്ന് പറഞ്ഞു. ഓക്കെ. ഓക്കെ സാർ, അപ്പം ഞാൻ ഫോൺ കട്ട് ചെയ്തോട്ടെ? ഇതിപ്പോ സ്റ്റാർട്ട് ചെയ്യുമ്പോൾ പറയുമോ എനിക്ക് എപ്പോഴാന്ന്? ഹലോ. Okay, good afternoon. Let us start the post-lunch session. Actually, I'm supposed to cover the entire electrostatics today. We were a little slow in the morning, so I'm starting with electric flux, and we will go to Gauss theorem and capacitors first. Then we will solve the some numericals. After that, in the evening session, and if time permits, in the afternoon session also, we will try to solve some numerical. So let us start with electric flux. So I think it is all familiar to you. Electric flux is the total number of electric field lines passing normal through any surface. And mathematically, it is the dot product of the electric field at that region and the area. So it is written as phi is equal to E dot ds, or we can say the dot product of two vectors is a scalar, so it is E ds cos theta. Phi is it is denoted by the letter phi, and the electric flux is E ds cos theta. And the total flux, to find the total flux, what we have to do is you have to integrate over the entire surface to extend our result for a larger surface. And this flux will be maximum when the angle between E and ds is 0, and cos 0 will be 1, and the flux will be maximum, and flux will be 0 when E and ds are mutually perpendicular to each other. And one more thing you have to remember, electric field has got its own direction, but the area we will consider as a vector, and the direction of the area is the outward normal drawn to that surface. The normal drawn from the surface in the outward direction is considered as the direction of area. Now, we will go to the unit. The unit of electric flux is actually voltmeter. So, voltmeter is the unit of electric flux. Now, there's a famous theorem called Gauss's theorem, which is something related to the electric flux. Let me go through the statement. The total electric flux through any closed surface is 1 by epsilon 0 times the charge enclosed by the Gaussian surface. So that surface is the total electric flux through any closed surface is 1 by epsilon 0 times the charge enclosed. And mathematically, it can be written as phi is equal to 1 by epsilon 0 into Q, where Q is the charge enclosed and phi is the electric flux. Or when we consider a small area ds, then we will find the E dot ds. Then to extend our result to the entire surface, we will consider the surface integral of the closed surface. Yes, E dot ds is equal to 1 by epsilon 0 into Q. By using calculus, we can write the expression like this. Now, if this is a Gaussian surface and if it encloses some charge in it, if it has 3 coulombs of charge inside, now the flux can be written as it is 1 by epsilon 0 into 3 coulomb. We can say 1 by epsilon 0 into 3 will be the flux. Now, if this has some other charges in it, 5 microcoulomb, negative 2 microcoulomb, plus 7 coulomb. So if it has this much charges inside, so we have to go for the total charge. So it will be 7 plus 3, 10, 10 plus 5, 15, minus 2, it will be 13, or we will write the flux as phi is equal to 1 by epsilon 0 into the total charge. That is 7 plus 5 plus 3, 15 minus 2, 30. So in that way, it depends only on the charges enclosed. The flux depends only on the charges enclosed. If there is no charge inside this Gaussian surface, definitely the flux will be 0 if it is not enclosing any charge. So you can expect some questions like this. So there will be two surfaces. Let us name it as S1 and S2. This surface is S1 and this surface is S2. And if there are 10 coulomb charge here, and here we have plus 5 coulomb charge. If you are asked to find the ratio of the fluxes through the first to the second, that is phi 1 is to phi 2. So we have to consider only the ratio of the charges. And S1 actually encloses this plus 5 coulomb charge and this plus 10 coulomb charge. Positive 10 and positive 5. Altogether, there will be 15 coulomb charge. So flux is 1 by epsilon 0 into 15. But S2 encloses only 10 coulomb charge. So flux will be 1 by epsilon 0 into 10. So the ratio will be 15 is to 10. It will be 15 is to 10, which can be simplified as 3 is to 2. So this is the ratio of the flux through these two surfaces. Such questions you can expect for your exams. So, okay. Now, we can use the Gauss theorem to find the electric field at a point due to different configurations. We have seen charges can be distributed over a line. It is called a line of charge. Again, charges can be distributed over a surface. And again, it can be in a volume. So we will see some applications. The first one is the flux through a line of charge. So this is a line of charge where positive charges are kept one after the other to get a long line. It is infinitely long. And I want to find the electric field at a point outside it due to the, by applying the Gauss theorem. We will consider a Gaussian surface like this. And we will consider elementary area ds on these 3 surfaces of the Gaussian surface. So we will imagine a surface to apply Gauss theorem. That surface is called the Gaussian surface. In the case of line of charge, normally we will go for a cylindrical Gaussian surface. It is not compulsory that we have to go for a cylindrical one. We can go for any other surfaces, but because of some symmetry, we are going for this cylindrical Gaussian surface. So we can find the flux passing through this one, this side A, side B, and side C. And you have derived this equation. It's a very simple derivation. I'm not going into the details. And we can apply Gauss theorem, and we can find the total flux. And we can also find the total charge enclosed. The total flux will be E into 2 pi RL. And the charge enclosed is lambda into L by epsilon 0, where lambda is the, I have already mentioned, it is the linear density of charge, from which we can get an expression for the electric field. It will be 1 by 4 pi epsilon 0, 2 lambda by R, or it can be written as lambda by 2 pi epsilon 0 R. In vector form, we can introduce a unit vector R cap there so that it becomes the electric field vector is given by 1 by 4 pi epsilon 0, 2 pi lambda by R into R cap. So already everybody know this derivation. Actually, it is very, very important. You can expect one for your board exams. Now, we will go for the flux, the electric field due to a sheet of charge. A sheet of charge is actually formed by keeping a large number of line of charge one after the other. So this is an infinitely long sheet of charge, or we can say the charges are distributed over a area, and it has a surface density of charge sigma. Again, here I am considering a Gaussian surface which encloses some charge, and it is also a cylinder. Here also the cylinder has 3 surfaces, namely A, B, and C. And we can apply Gauss theorem, and we can find the individually the fluxes passing through this face and the flux passing through this one and the curved surface. Finally, we will add, and we will get the total flux as 2E. The total flux can be calculated, and again the total flux will be 2E into pi r square, and we can find the total charge enclosed, that will be sigma pi r square. It is multiplied with 1 by epsilon 0, from which we can arrive an expression for the electric field is sigma by 2 epsilon 0. The important thing is the electric field around a thin sheet of charge depends only on the surface density of charge. It depends only on sigma. It does not depend upon the distance of that point from the sheet of charge. Everywhere it will be same, and it is sigma by 2 epsilon 0. We can write it in the vector form like this. We can introduce the vector unit vector I cap because it is acting in the positive x direction in the shown figure. So we can, because this is the positive x direction, and that's why we have used I cap, or simply if you consider the distance, you can say it as R cap, whatever it may be. It doesn't matter. Since it is acting in the positive x direction, our figure, so we have written it as I cap. Okay. Now, another important thing, and this is actually very important. So how to find the electric field due to 2 closely spaced thin sheet of charges. This is a thin sheet of charge with a sigma, and this one also with a density sigma, or I can call it a sigma A, and this one sigma B. Let it be the surface density of charges. Both are charged with the same density, and both have positive charge. So let us say, let us see what happens. I'm considering a point P here in between the 2 plates. So I am going to find the electric field due to the first charge of first sheet of charge. So the expression was sigma by 2 epsilon 0. So I will write it as sigma A by 2 epsilon 0. And what will be the direction? If you keep a positive charge here, definitely the positive charge on this sheet will repel it. So the electric field will be in this direction. Now we can find the electric field at the same point P due to the second sheet of charge, sigma B. It will be sigma B by 2 epsilon 0. And in which direction it will be acting? Because if you keep a positive charge here, this is positively charged, so it will be acting in the opposite direction. So the resultant electric field will be the difference between the two, that is sigma A by 2 epsilon 0 minus sigma B by 2 epsilon 0. And what will be the case on this side? If the point is on this side, what will be the case? Here also, this positive charge will repel it. So it will be sigma by everywhere. It will be sigma A by 2 epsilon 0 with respect to the first one. And for the second one, it will be again sigma by 2 epsilon 0, sigma B by 2 epsilon 0. I have told that everywhere the electric field will be having the same value. So, and in this case, if you keep a unit positive charge here, it will be repelled by both of them. So these two will be added up and the resultant field will be in this direction. And it will be, we can call it sigma A plus sigma B by 2 epsilon 0. The same is the case here, but with a slight difference. It will be negative sigma A by 2 epsilon 0. And here it will be negative sigma B by 2 epsilon 0 because both of them are acting in this direction. And the resultant will be negative of sigma A plus sigma B divided by 2 epsilon 0. Now, let us imagine if sigma A and sigma B are equal. If they are equal to sigma, both of them have the same surface density. So what will happen? Inside it will be sigma A minus sigma B by 2 epsilon 0. But sigma A and sigma B are equal. So sigma A minus sigma B will be 0. So there won't be any electric field in between the two plates. And here it becomes double. Here also it becomes double. So this is very important. Now, one more thing we can deduce from here. If the first plate is, which is also very important, we have some application with the capacitors. If the first plate has a surface density sigma A and the other one has negative sigma A, what happens? This is sigma A by sigma minus sigma B will come and both are same. So sigma minus sigma, sigma minus negative sigma. So they will be added up and the resultant electric field will be inside the region when the first plate is positively charged and the second one is, this is positively charged and this one is negatively charged. So we will have sigma by epsilon 0. This will be the electric field in between, but outside it will be 0. This is very, very important when we go for capacitors. Okay. Now we can, so if we have two plates which are charged with the same surface density sigma, and if both are positively charged, the region between the plates, the electric field will be 0, and outside it will be sigma by epsilon 0. We can conclude like that. If one is charged with a positive sigma and the other sheet has a charge negative sigma, then the electric field will be confined to the region between the two plates. And outside it will be 0. Here it will be sigma by epsilon 0. This side it is 0. And here also it will be 0. That is the conclusion. It is actually very important. Now let us see the expressions for the in the case of a charged spherical shell. This is a charged spherical shell where the charge is, it is a shell of negligible thickness. So the entire charge will be distributed over the surface. Sigma is again the surface density of charge. So you have to derive the expression for the, we can consider three regions, one inside it, then outside it, and on the surface. So we have to derive the expressions for the electric field at a point inside this charged sphere and also outside it. The derivation you can first, we can consider a point which is outside it. So you can see this figure. So this is the spherical shell. It's a hollow spherical shell. It has charges Q on it with a surface density sigma. Now, I want to find the electric field at this particular point, that is P, which is at a distance from the center. That distance is denoted here. Small letter r is the distance of this point from the center of the spherical shell. Now, this spherical shell has a radius of capital R. Now, let us consider a very small area ds, infinitesimally small area ds on the surface. And as I have mentioned earlier, the area is directed outwards. ds will be the area. And at this point, definitely the electric field will be radially outwards. We know that the electric field lines will be coming out from a surface normal to it. It will be coming out of a surface and normal to the surface. So this will be the direction of electric field. So we can find E dot ds. Here it will be E ds cos 0 because ds and E are in the same direction. ds and E are in the same direction. So it will be E ds. And it is integrated over the surfaces. And one more thing, we can see this is the Gaussian surface, which is a concentric sphere with a spherical shell with the center at O. And all these points will be at the same distance from the center of the charged spherical shell. All the points on this dotted surface will be at the same distance from the center of the sphere. So, at each and every point on the surface, the electric field will be same. So E remains a constant. So when you integrate, when you find the total flux, we got the flux as E dot ds. So to find the flux due to the entire surface, I'm going to integrate it over this surface. So E is, I have mentioned that E is a constant everywhere on the surface. So phi E will be E integral ds. ds is a small elementary area on the surface of this sphere. So I will consider this entire Gaussian surface is made up of such a small ds's. So when I join all these ds's together, I will get the entire surface area of this spherical shell. And that will be, we know what is the expression for the surface area of a spherical shell, outer surface area of a sphere, where radius is smaller. So this is ds, another ds, another ds, another ds. In that way, we can make the entire surface. So that integral will give you 4 pi r square. So we can substitute that value here. So E into our integration, this we will give to 4 pi r square. That's equal to Q by epsilon 0. What is Q? By Gauss theorem, it is the total charge enclosed. And we know that this charge Q is distributed over this spherical shell whose radius is capital R with a surface density sigma. So Q is equal to, in unit area, we have sigma charge. So over this surface whose area is 4 pi capital R square, Q is distributed. So Q is equal to 4 pi R square into sigma. Now we can apply Gauss theorem. We can equate these two. How? Total flux is equal to 1 by epsilon 0 into the charge enclosed. And on simplification, we will get the expression for electric field as Q divided by 4 pi epsilon 0 R square. So this is the expression for the, capital R square divided by small r square. Capital R square is missing here. So Q into capital R square divided by 4 pi epsilon 0 small r square will be the electric flux. Now, we are going to find the electric field at the interior of this surface. So let us consider the Gaussian surface inside it. So I am going to, let us consider this as the charged spherical shell, this bigger one as the charged spherical shell. This is a charged spherical shell. and I'm considering this point P, which is inside it, and I want to find the electric field at this particular point. So how can we find the electric field there? So through that point, again, we have to describe a Gaussian surface. Here we have to consider a Gaussian surface through this P, and its center is O. As usual, this radius is R, and this one is capital R. Now, we can say the flux will be, we can calculate the flux, how we can find a small area, and let us imagine that the electric field is there. So EVE into 4 pi r square will be the flux. After that, when we apply the Gaussian theorem, we know that the flux passing through the surface is depending only on the charges enclosed by it. So what will be the charge enclosed by this Gaussian surface? This is the charged spherical shell. All the charges are residing on this surface of this shell. And the Gaussian surface which we have considered is well inside it. So inside this Gaussian surface, there is actually no charge. So this Gaussian surface is not enclosing any charge. So we can say the electric field will be definitely E into 4 pi r square. If you say that the flux is E into 4 pi r square, that's equal to 1 by epsilon 0 into Q. Since the Gaussian surface is not enclosing any charge, it will be equal to 0. So we can say, since 4 pi r square is not 0, E will be equal to 0. So the electric field inside a charged spherical shell is 0. So this is a very, very important result. So if you have a any metallic object like this, hollow object, which is charged inside it, the electric field will be 0. So if you want to protect some sensitive devices from electric field, what we have to do is just keep it inside a hollow metallic sphere. Whatever may be the charge outside or whatever may be the field outside, inside that hollow shell, the electric field will be 0. And this phenomenon is actually called electrostatic shielding. Okay, that's all about Gauss theorem. Now, this I have already mentioned. This is called electrostatic shielding. Electric field inside a charged hollow conductor will be always 0. So this is the picture of a car. And even though the lightning strikes the car, the passengers inside it will be safe. If they are well inside, or if they are sitting like this inside a room, if they are sitting inside away from the walls, both of them will be, this passenger and this person will be safe, because even though the charges are passing through this car, the electric field inside it will be 0. So they won't be affected. So you will be, if you are traveling by a car, if there is a lot of lightning, what you can do, you can just stop the car and sit inside it. You will be safe. It is because of electrostatic shielding. So these two figures just explain that. Now we can see a small problem here. How to find that we will see later. Okay, we will finish some of the remaining topic. So that's all about Gauss's theorem and applications. Actually, we have 3 applications. One is how to find the electric field at a point due to a line of charge. Then we have to find how to find the electric field near a point near a thin sheet of charge. Then what will happen if you have 2 parallel sheets with the same surface density of charge and opposite surface density of charge? Then we have to go for a spherical shell, how to find the electric field inside it and outside it. Now we can go to the next topic, that is potential and capacitors. Are you able to see my presentation? I'm sharing it. Are you able to see the presentation, the new slide? Okay. So we will move to the electrostatic potential and capacitance. That's the second chapter actually. I was going a little fast because I had to finish entire electrostatics by 2 days. Okay. Now, what do you mean by electrostatic potential difference between 2 points in an electric field? It is actually defined as the work done in bringing a unit positive charge from one point to the other. Actually, this should be done without any acceleration of the charge. So electrostatic potential difference between 2 points is defined as the work done in bringing a unit positive charge from one point to another. So that much work done will be the difference in the potential energy, electrostatic potential energy of the charge at those two positions. Now, if I have done W unit of work to bring a charge capital Q from one point to another in an electrostatic field. I'm bringing a charge capital Q from one point to the other, and for that I have done W unit of work. To bring Q coulomb of charge, I have done W unit of work. So the by the definition of potential difference, it is a work done to bring unit positive charge from one point to another. For Q charge, I have done W work. So what is the work done in bringing unit charge? Or the potential difference will be the total work done divided by the total charge. So it will be W divided by Q. The potential difference between those 2 points will be the total work done W divided by the total charge which was shifted from one point to another. So we will get the work done in shifting the unit charge. And the SI unit of potential difference is joule per coulomb because work is measured in joule and charge is measured in coulombs. Therefore, the SI unit will be a joule per coulomb. And it is known as volt. Joule per coulomb is called volt to honor our gate scientist volt. And how can we define 1 volt the SI unit? How can we define it? So if I bring 1 unit positive charge from one point to another, I have done 1 joule of work. Then I can say that the potential difference between the 2 points will be 1 volt. If you have 2 points, A and B, and I am shifting or I am moving 1 coulomb of charge from A to B. For that, I have done only 1 joule of work. So what is the potential difference between these two? Definitely, it will be work by charge. So 1 by 1, it will be equal to 1 volt. So 1 volt is the potential difference between 2 points if 1 joule of work is done in moving 1 coulomb charge from that point 1 to the second. That's the definition of as a unit of potential difference. Now, let us try to derive the expression for the potential at a point due to a point charge. Potential at a point due to a point charge. So that is a lengthy derivation. Actually, if it is required for you, can you please respond if the derivation is required, or just I go for the equation? You can type it in the chat box. If derivation is required, we will go for that. Okay. One group told they required it. They require it. What about others? Please make it fast. Okay. So let us consider the point O where I have kept Q unit of charge. Now there is another point P which is at a distance R from the point O where I have kept a charge capital Q. A capital Q is kept here and I am assuming that this charge Q is greater than 0. What does it indicate? If you say a charge is greater than 0, it means it is a positive charge. So a positive charge is kept here. at O, and I'm considering a point P which is at a distance R from it. Now, let us consider another point P dash here. Now, P is at a distance R, and P dash is another point which is slightly away from it. And the distance of the point P dash from this O is R dash. It is written as vector R dash. So this point P dash is at a distance R dash from this point O. Now, I am moving this a charge, unit positive charge from P dash towards this direction by a small quantity dr dash. So dr dash is a small displacement of this charge which is kept at P. I have already kept a unit positive charge here at P dash. I have a unit positive charge, 1 coulomb positive charge is kept here, and it is displaced from P dash in this direction by a small displacement dr dash. Now, we can see what is the work done for this. Actually, this point P dash is a point which is slightly away from this V, or we can say it is from, we are bringing this from a larger point which whose distance is R2 to a point whose distance is R1, or it is far away from this P. So I am considering, I'm bringing it far away from P, and this P dash is an intermediate point between P and the my place where I am bringing this charge. And so at this point P dash, because of the presence of this charge here, Q, there will be a electric field, or this experiences a force here, and that force is given by 1 by 4 pi epsilon 0 Q by R dash square into R dash cap. Actually, we are keeping a unit positive charge here. So that is why that other charge, the plus 1 charge is kept here. So 1 by 4 pi epsilon 0 Q1 Q2 by R square. Q1 is capital Q and Q2 is 1 coulomb. So F will be 1 by 4 pi epsilon 0 Q by R dash square into R cap, R dash cap. So this is the unit vector along OP dash. Now, it is displaced by a small quantity R dash to R dash plus D. I am considering this destination as R dash and this point as R dash plus dr dash I am considering. So from here, I am bringing it towards this direction. dr dash plus dr dash I have taken. So what will be the sign of this dr dash? Definitely it will be negative. Why? Because it is R dash and this one is, when I write this point, the position vector of this one as R dash plus dr dash, actually it is dr dash less than R dash. I think it is clear. So when I keep it at P dash, when it is kept at P dash, the distance will be R dash. Now I am displacing it towards P by a small amount dr dash. So now this distance has reduced. So that's why I have written this R dash plus dr dash, but the sign of dr dash will be negative. So a small amount of work has to be done for that. And that work done will be dw is equal to, this negative sign came because it is written as R dash plus dr dash, and dr dash is negative. Negative 1 by 4 pi epsilon 0 into Q by R dash square into dr dash. This is the dot product of force and displacement. You know how to find the work. Work is the dot product of force and displacement. So 1 by 4 pi epsilon 0 Q by R dash square is the force and negative dr dash is the displacement. So this is a small amount of work done in displacing this charge from P dash by slightly to a point dr dash. Now, I want to find the total work done in displacing this charge from a large point, which is at a very large distance, where the electric field is 0. There the electric field has no influence. So I'm bringing this charge from a place where the electric field due to that point charge is not influenced. So I consider that point as infinity. So I'm bringing it from infinity to this point R. Therefore, the work done for that is written as integral. Sorry, I have told you that the small amount of work done is dw. So the entire path from infinity to R dash can be divided into small segments of length dr dash. So when I add, I can find the work done for the small dr dash first, then the next dr dash, then the next dr dash. In that way, I can calculate the work done in each and every small displacements. And finally, when I add all of them, I will get the total work done. So instead of doing all those things, we have a technique. We have to integrate the small amount of work done within the limit. We are starting the procedure from infinity and we are ending at R. I am bringing it from infinity to the position P we have already seen, that is R. So I am integrating it from infinity to R dw. So W is equal to infinity to R. I am going to substitute the values of this dw. You have already seen it. Negative 1 by 4 pi epsilon 0 Q into dr dash divided by R dash square. So that integration process, no need of writing entire processes. So since Q and all these things are constants, so we are integrating it from infinity to R 1 by R dash square dr dash. Only this R dash is the variable. So what is integral 1 by R square dr? What is integral 1 by R square dr? Math students may be knowing that it is negative 1 by R. So we are using that result here. It is negative 1 by R, and we have to apply the limit. The lower limit is infinity and the upper limit is R. So when you apply this limit and simplify it, you will get the expression as 1 by 4 pi epsilon 0 Q by R. So this is the total work done in bringing 1 coulomb charge from infinity to the point P where it is now. So when I do this much work, the charge is brought from infinity to the present position. Now, actually, how we have defined potential difference? It is a work done in bringing a unit positive charge from one point to the other. That work will give you the difference in the potential of those 2 points. Now, what is the situation here? I am bringing this charge from infinity. What is the speciality of infinity? At infinity, electric field is 0. So electric potential is also 0 at infinity. From there only I am bringing it. And now I have reached my present position. The charge has reached its destination. So what is the work done for that? 1 by 4 pi epsilon 0 Q by R. So actually what it is a work done in bringing unit positive charge from infinity to its present position. So by definition, it is the potential difference between infinity and the point P. I think it is clear. Potential difference is defined as the work done in bringing unit positive charge from infinity, one point to another point. But now we have selected one point as infinity and the destination as a particular position R. And I calculated the work done in bringing it from infinity to that position. So it will be the potential difference between infinity and that point. What is the speciality of infinity? Its potential is 0. So what is this potential difference? This potential difference will be 1 by 4 pi epsilon 0 Q by R. So I am subtracting A minus B. If B is 0, what is A minus B? I am finding the difference of 2 numbers, A and B. A minus B is, I got A minus B. But if B is equal to 0, what will be A minus B? Definitely it will be equal to A. Similar is the case. I am bringing it from a place where potential is 0 and the present place the potential has a value. So the difference will be equal to the potential of that particular point. And that's why we will call this one as the expression for the potential at a point which is at a distance R from a charge Q. So this is the expression for the potential at a point due to a point charge. Similarly, we have derived the expression for the electric field at a point in the morning session. It was E is equal to 1 by 4 pi epsilon 0 Q by R square. But this is potential is 1 by 4 pi epsilon 0 Q by R. So we can have a comparison. Electric field is inversely proportional to the square of the distance, but potential at a point is inversely proportional to the distance R. That is the difference. So E is equal to 1 by 4 pi epsilon 0 Q by R square and V is equal to 1 by 4 pi epsilon 0 Q by R. Okay, by similar procedure, if we fix the limits as R1 and R2. So we are starting from R1 and we are ending at R2. So 2 points. One is at a distance R1 from the point charge. Another one is at a distance R2 from the point charge. And when you find or evaluate the work done in that case, you will get the potential difference between those 2 points. So that derivation you can do by yourself. I think it is exactly similar to what I have already discussed. Only one difference here, we will apply the limit as R1 to R2 or R2 to R1, from where we are starting. I am starting from R2 and ending at R1. So I will apply the limit at R2 to R1. So the integration process will give you the result as 1 by 4 pi epsilon 0 into 1 by R1 minus 1 by R2. This equation you can derive by yourself since you have learned how to derive the expression for the potential at a point. Now, it is very clear that potential difference between 2 points is the work done. So in 11th class, we have learned work done is independent of the path. And it depends only on the initial and final positions. If you do work against a conservative force. Here also we have seen that the work done is depending upon the positions R1 and R2. The final expression was 1 by R1 minus 1 by R2. So we can say that the electrostatic potential difference between 2 points is also depending only on the initial and final positions. It is independent of the path through which we are displacing this charge from one point to another. So we can say the electric field is conservative in nature. What do you mean by conservative force or conservative nature of a force? If the work done by a force is independent of the path, or we can say if the work done by a force over a closed path is zero, in these two can be called the conservative nature of force. So we can conclude that the electrostatic field is a conservative. Electrostatic field is conservative in nature, or electrostatic force is a conservative force. Or we can say the work done by electric field over a closed path will be always zero. Now we can have a comparison of the variation of electric field and electric potential with the distance. So this blue graph shows the electric potential with a distance due to a point charge. And you know the expression. What is the expression? 1 by 4 pi epsilon 0 Q by R. So blue line is variation of V with the R, and E. E is, what is electric field? What is the expression for the electric field? E, 1 by 4 pi epsilon 0 Q by R square. And this shows the variation of electric field with the distance. And if you observe carefully, you can see a point where these two graphs are intersecting each other. At this point, you can see, I can mark it here. So the graph of the variation of potential with the distance and electric field with the distance are intersecting. Can anybody type what will be the distance of this point from the charge, where it will happen? So at a point, these two graphs are intersecting each other. So this is the point. So can you, from the expression, can you tell me what will be the distance of that point from the charge? One is electric field is 1 by 4 pi epsilon 0 Q by R square. I will write the expression here. You will be able to solve it. Electric field is 1 by E is given by 1 by 4 pi epsilon 0 Q by R square. Potential is 1 by 4 pi epsilon 0 Q by R. And what is the meaning of these two graphs are intersecting? These two are not equal. Their magnitudes are equal. Electric field, whatever may be the magnitude of electric field, it must be equal to the magnitude of the value of the electric potential. That is the meaning of intersecting. At this particular point, value of V and value of E, those numerical values are same, but we cannot equate them because one is work, another one is a force. They are two different physical quantities. We can't equate them, but their values are same. Numerical values are same. Can anybody type it in the chat box? What will be the distance of that point when these two happens? 1 by 4 pi epsilon 0 Q by R square and 1 by 4 pi epsilon 0 Q by R must be same. Nobody is responding. Very simple. Just think. this Q by R square and Q by R are equal. If you observe this, observe the graph. Are you able to see the graph? Hello, children. Are you able to see the graph? Please type us if you are seeing. I got one answer. They told that distance is 1 meter. One answer I got. It is, again, one more answer. Very good. Your answers are correct. It is 1 meter. Why? Why it is 1 meter? A lot of answers are coming now. Why it is 1 meter? Because R square, that is, if R is 1, the square of 1 meter is 1 and R is also 1. 1 square is equal to 1. So these two things will become equal. Once it has asked for one board exam, so keep it in your mind. What is the speciality of this point P? E and B are same, having same value, and that point is at a distance of 1 meter from the source charge where the charge is kept. And this graph is also important. Now, how to find the potential at a point due to two charges? So this is very simple. Why? Because potential is the work done. So it is a scalar quantity. No need of going for any vector addition. They are simple numbers. So we have two charges, Q1 and Q2 at P and Q. So there is a point O, which is at a distance R1 from Q1, and it is at R2 from Q2. So what is the potential at this point O due to these two charges? Q1, it will be 1 by 4 pi epsilon 0 Q1 by R1. Here it will be 1 by 4 pi epsilon 0 Q2 by R2. So when we add them, it becomes V is equal to simply V1 plus V2, because potential is a scalar quantity. It has no direction, so we can directly add them. So it is 1 by 4 pi epsilon 0 Q1 by R1 plus 1 by 4 pi epsilon 0 Q2 by R2, or simply 1 by 4 pi epsilon 0 into Q1 by R1 plus Q2 by R2. So when you do numericals with electric field and electric potential. So when you add electric fields, you have to consider them as vectors and you should find the resultant. But when you add potentials due to two charges, no need of considering them as vectors. They are scalar quantities, so that you can directly add them. Okay. It's a very lengthy derivation, and I'm not going to in details of that one. So we will move to the next topic. I will tell you only the final expression. Are you able to see the screen? Are you able to see the slide? Okay. We will go to the final expression only. That expression is important. The potential at a point anywhere around a dipole, electric dipole, is given by V is equal to 1 by 4 pi epsilon 0 P cos theta by R square. I will tell you what are these things. So this is an electric dipole. Let me draw it here. It's an electric dipole. We have a point P here, which is at a distance R from the center of the dipole. From here, it is at a distance R. Let me note this one. And the potential, then this angle is theta. This is negative Q. This one is positive Q. And the potential at this point is given by 1 by 4 pi epsilon 0 P cos theta divided by R square. P is the dipole moment, and theta is the angle between this R and the dipole moment, and it is 1 by 4 pi epsilon 0 P cos theta by R square. Now, what will be the expression for the potential at a point on the axial line? That equation we should deduce from this. If this point is here, So what happens? This point comes back to here. So this is the line joining. So what is the angle between P and this line? Definitely theta will be 0. So cos 0 is 1. So potential will be 1 by 4 pi epsilon 0 P by R cube. Sorry, P by R square. It will be P by R square. Now what will happen if this point is somewhere here on the equatorial line? So this point is going from here and finally this angle becomes 90 degree. So the potential at a point on the equatorial line will be P cos 90. Cos 90 is 0. So the potential will be 0. Remember that all the points on the equatorial line of an electric dipole will be at 0 potential. All the points will be at 0 potential along the equatorial line. Keep this in your mind. Okay, you can go through this. Whatever I have told. V is equal to 0 on the equatorial line and V is equal to P by 4 pi, 1 by 4 pi epsilon 0 P by R square. This is along the axial line. Now, we have to see what is meant by electric energy of a system of charges. So, what is meant by electric energy of a system of charges? So, it is defined as the work done in bringing them from infinite separation to the present position. So, if we have some charges located at different areas, let me say Q1 and Q2 and Q3. They are located at 3 different points A, B, and C. And this is our origin of coordinate system. So the point A is at a distance R1, we can say this one is at a distance R2, and this one is at a distance R3 from O. Now, to arrange these 3 charges here, to bring them from infinity to their respective positions, we have to do some work. So that much work done will be stored in these 3 charges together in the system of these 3 charges in the form of potential energy, or it is called the electric potential energy. So it is defined as the electric potential energy of a system of charges is defined as the work done in bringing them from infinite separation to the present position. Or we can simply define in this way also. It is a work done to take these charges from their present situation or present position to infinite separation. Actually, this you will be learning in chemistry when you learn about the bonds. There is an application of this. So we can consider a system of charges. So we will derive this expression. Is it required derivation? Again, I'm asking, do you require the derivation of this potential energy of a system of some 2 or 3 charges? No answer. Again, answer is yes. It will be difficult if you go like this. Okay. Okay, we can go into, we can derive the electric potential energy of a system of charges. First, let us try to find the potential energy of a system of 2 charges, namely Q1 and Q2. So in the beginning, they are at infinite separation, and now we are bringing them from infinite separation to their present positions. So whose position vectors are R1 and R2 respectively. Okay, now we will go to the next. Okay. This is the coordinate system. Here, this is the position where I want to bring the charge Q1 from infinity. This is our origin axis. So this distance is, let me say it is R1. And there is another one, it is Q2. The second charge is to be brought here. And this one is at a distance R2. Okay, and one more thing, remember that we are conducting this in a field-free region. Initially, there is no charge in the vicinity of this, this origin. We don't have any other charges in this area. So one by one, I am going to bring these charges from infinity to their present position. So in the beginning, imagine Q1 is at infinity and Q2 is also at infinity. So let me bring the first charge Q1 from infinity to R1. So there is no electric field. There is no potential at this point because all of them are at infinity. And I am bringing this charge Q1 with from infinity with the constant velocity to R1. So what is the work done for that? There is no other charge nearby. Only one charge is there, Q2, and which is at infinity. So it will not have any influence on this Q1. Both of them are, this is infinity at this side, the other one is infinity at the other side. So what we can say, no need of doing any work to bring Q1 from infinity to this point. So that work is written as W1. So W1 is equal to 0. The reason is there is no other charge or no other electric field in this region. If there is an electric field in this region, then this point may have a potential, this point may have another potential, then the scenario will be different. But we are dealing with a region where there is no electric field. So first Q1 is brought from infinity to this point and work done is 0. Now I am going to bring the charge Q2, but situation is different. So this point where I am supposed to bring the charge Q2 is at a distance R12 from the charge Q1. Q1 is here now. Q1 has already brought, Q1 is already brought from infinity to this point, so it is there. Therefore, when I am bringing this Q2 from infinity to R12, there is an electric field produced by the charge Q1 everywhere. Yet now there is an electric field, and this charge will produce a potential at this particular point, and which is written as V1. That charge produces a potential at that point Q2. It is written as 1 by 4 pi epsilon 0 Q1 by R12. Potential at a point due to a point charge. So this is a point which is at a distance R12 from Q1. So V1 is 1 by 4 pi epsilon 0 Q1 by R12. Now, we have already defined the potential difference as V is equal to what you have written, W by Q. So what will be W? V is W by Q. So W will be definitely V into Q or Q into V. Now, we have a potential at this point, which is called V1. So into that potential, I am bringing another charge from Q2 to this. So I have to do some work. That work will be potential at that point multiplied by the charge. So it is V1 into Q2. What is V1? I have written here 1 by 4 pi epsilon 0 Q1 by R12 and it is multiplied with Q2. So our result is 1 by 4 pi epsilon 0 Q1 Q2 divided by R12. So what is the total work done? To bring the first charge, the system consists of two charges. First charge is brought without the expense of any work. That is zero work. But second one, we need some work and it is given by 1 by 4 pi epsilon 0 Q1 Q2 by R12. So the total work is W1 plus W2, which is equal to 0 plus this one. And finally, the total work done is 1 by 4 pi epsilon 0 Q1 Q2 by R12. And this is called the potential energy of system of these two charges. That's the derivation. Now, if there are three charges, what will happen here? Again, we can follow the same, you can think and you can write on your book itself by yourself. Q1 is brought here, no work is done because Q2 and Q3 are at infinity. So W1 is equal to 0. Then again, we are bringing Q2. For bringing Q2, we have to do some work. Just a minute. Hello? Hello, am I audible? Hello, excuse me, am I audible? Sorry for the interruption. I lost the connection in between. I will continue now. Okay. Okay, is the screen visible to you? Is the screen visible to you? If so, please type us. Okay, thank you. So let me continue. So we were discussing the potential energy of a system of three charges. So we have Q1, Q2, Q3. So first we have to bring Q1, but remember that Q2 and Q3 are at infinity. So what is the work done in bringing Q1? What will be the work done in bringing Q1? Q2 and Q3 are at infinity, so no need to do any work. So we can bring Q1 without doing any work. So W1 will be 0. Then I'm going to bring Q2 now. That we have already done it. Like W2 will be equal to the potential at this point due to the charge Q1 multiplied by Q2. That is V1 into Q2. This we have already done. It will be 1 by 4 pi epsilon 0 Q1 Q2 by R12. Now we have to bring the third charge Q3. Now what is the difference? When I want to bring the charge Q3, I have to do work against the existing electric field of Q1 and also of Q2. But Q3 is at a distance R13 from R13 from Q1 and R23 from Q2. So we have to calculate the potential at this point Q3 due to the charge Q1, multiply it with the Q3. Is it clear? We have to calculate the potential at this point due to the charge Q1. Then we have to multiply that potential V1 with the Q3. Then again, we have to calculate the potential at Q3 at this position due to the charge Q2. Let me call it as V2. And it should be multiplied with the Q3. So we have to do work against the potentials of Q1 and the potential of Q2. So in 2 steps, we can do it. So W3 will be equal to Q3 into V1 plus Q3 into V2, where V1 is the potential due to the charge Q1 and V2 is the potential due to the charge Q2. So it will be 1 by 4 pi epsilon 0 Q1 by R13 plus 1 by 4 pi epsilon 0 Q2 by R23. There will be 2 terms. So we have calculated the work done to bring the first one. Then we have calculated the work done to bring the second one. And finally the third one. So the result will be sum of W1, W2 and W3. It will be this one. 1 by 4 pi epsilon 0 Q1, Q2 by R12. There is a way to remember this. Q1, Q2 by R12. Q1, Q3 by R13, Q2, Q3 by R23. And if there is a one more charge, we have to write the work done to bring that Q4 against Q1, Q4 against Q2, Q4 against Q3. 3 more terms will come. So in that way, we can extend this result for any number of charges or a system of any number of charges or any number of charges we can derive it. Okay, now we will move to a new concept which is called equipotential surfaces. Equi means equal. Potential means we have learned about potential. So equipotential means the potential will be same everywhere. So let us consider a charge Q situated here. We have a charge Q kept at this point. So if I calculate the potential at this point P due to this charge, it will be 1 by 4 pi epsilon 0 Q divided by R. And again, I will consider another point here, which is at the same distance from this charge Q. Again, the potential will be 1 by 4 pi epsilon 0 Q by R. We can say this in the case of potential because potential is a scalar quantity. But we cannot say that electric field at this point will be equal to electric field at this point. We can't say like that. We can't equate them because they are one is acting in this direction and the other one is acting in the another direction. But the potential will be same at this point. The potential will be same here. And in every point over this circle, the potential will be same. Now let us imagine this point Q in space. And consider that this point Q is in space and imagine all the points around it which are at the same distance. So all those points together will give you a spherical surface. What is the speciality of that spherical surface? All the points on that spherical surface will have the same potential. And it is given by 1 by 4 pi epsilon 0 Q by R. So such a surface is called an equipotential surface. So an equipotential surface is a surface where all the points on it will have the same potential. Now, this is the picture which show the equipotential surfaces around a positive charge and it around a negative charge. All are concentric spherical surfaces. So this figure shows the equipotential surfaces. These blue lines, these blue dotted lines will give you the equipotential surfaces around a dipole. And this one, these blue lines will represent the electric field. They are parallel. So definitely it is a uniform electric field. And the equipotential surfaces are planes. These are the different types of equipotential surfaces for different configuration. This is for an isolated positive charge. This one is for an isolated negative charge. This is for a dipole. These are the equipotential surfaces. You can see this. All these are the equipotential. This will show the electric field lines. And these are the equipotential surfaces in a uniform electric field. So it depends upon the configuration. Shape of the equipotential surface depend on the configuration. Now we have to see some important properties of equipotential surfaces. The most important property is electric field lines will be always perpendicular to the equipotential surfaces. The always electric field lines will be perpendicular to the equipotential surface. Similarly, work done in moving a charge from one point to another point in an equipotential surface is zero. Why? I have to take one charge from one point to another. This is an equipotential surface. Let us imagine this is an equipotential surface. Here I have a charge, and here I have another. Sorry, here I have a point P, here I have a point Q, and I am shifting a charge from P to Q. Here the potential is V. At this point, potential is V. At this point is also potential is V. That's why it is called equipotential surface. So what is the potential difference between these 2 points? V minus V, it is 0. The potential difference 0 means work done also will be 0. Now, for a point charge, there will be concentric spheres. And due to electric field, there will be planes normal to the electric field. And in uniform field, those will be parallel planes. Okay, that is all about equipotential surfaces. And you can expect some questions like this. We have a point charge at a particular point, and you are considering 2 points at equal distance from that point. So I will tell one simple example. Here we have a charge Q, and at a distance R1, I have a point P1. At the same distance R2, I have a point P2. Then I have to shift it from P1 to P2 like this, like this, like this. What is the work done in all these cases? This is a charge Q. There is no other charge in the surrounding. This is at a distance R1. This point P2 is also at the same distance R1 from Q. So P1 and P2 will be at the same potential. Or we can say the P1 and P2 have equal potential. So potential difference will be 0. So work done to move a charge from P1 to P2 along this path is 0. Along this path also is 0. Along this path also it is 0. So keep it in your mind. If we have 2 points on the equipotential surface, if we displace a charge from one point to another through any path, you can see the work done will be 0. So that is the importance of the equipotential surface. Based on this, we will be doing some numericals in the evening, definitely. Okay, now we will move to the second part of this chapter, a device which can store the charges in it, or a device which can store the electrostatic energy. So a capacitor is a system which consists of two conductors separated by an insulator. So when a charge Q is given to a conductor, and there will be a potential around it, let it be V. And I am telling that the potential is given by, if I have given a charge here, and if I have point P here, that potential is given by, at this point is given by, we have seen that equation many times. V is equal to 1 by 4 pi epsilon 0 Q by R. So if I going on increasing the value of Q, what will happen to the potential? V is equal to 1 by 4 pi epsilon 0 Q by R. I'm not changing the point. Instead of that, I'm increasing the charge. V also will be increasing. So we can say along with Q, V also will increase. So they are directly proportional. So we can say Q and V are directly proportional. When Q increases, V also will increase. So Q is equal to a constant C into V. And this constant is called the capacitance of that particular conductor. If it is a capacitor, we can call it the capacitance of the capacitor. Or if it is a body, we can call it as the capacitance of that body. And then we can say C is equal to Q divided by V. And these are different types of capacitors. You can see this is a electronic circuit board, and you can see this is a capacitor. You might have seen it. This one is a capacitor. All these are different types of capacitors. And here also you can see different types of capacitors. This is a type of capacitor. This is called ceramic capacitor, polyester capacitor. This is another capacitor, electrolytic capacitor. So different types of capacitors you can see in all the electronic circuits. They have got a wide range of applications. So how can we make a capacitor? Here also you can see different types of variety of capacitors which are used for many purposes. So this is the symbol of a capacitor. Two parallel lines of equal length, and there they have connection wires. This is somewhat similar to the symbol of a cell, but in the case of cell, one line will be larger than the other. But here these two lines will be of equal length. Now, how can we construct a capacitor? So let us consider a metallic plate, and it has got a charge Q on it. This much positive charge is there. We have charged or electrified this metallic plate to this much charge. And if we again give more charge to this, the potential will increase. We know the potential is proportional to the charge. So when you give more and more charges, the potential also will increase. And finally, there is a maximum limit. It can hold that much amount of charge. After that, if you again charge it, the potential will become very high. The electric field in the surrounding region will become very high. It will ionize the air, and this charge will be leaking from this plate. So there is a limit up to which we can store charges in it. So is there any possibility to increase the capacity of this conductor to store more charge? How can we make it store more charge? So for that, if I keep a very similar metallic plate very close to this one, the first one, what will happen here? In the morning we have Z. So a positively charged plate is kept here, and we have brought another plate to very close to it. So definitely negative charges will be induced here, and positive charges will be induced on the other side. It will happen. So negative charges are formed on this side. I think you will be able to see this. It is blue in color, and positive charge will be formed here. So this one has got a particular potential now. Now we have some negative charge here. Let us say this negative charge is, the negative charges formed here is negative Q. And all these charges together will produce a potential around this. Q charges are there. And if this distance is R, from this side to this one, if this distance is R, I can say, if such a single charge is considered, 1 by 4 pi epsilon 0 let me say negative Q by R. That will be the potential due to a charge. So here, these charges are positive. So charges are at a positive potential V. Now, these negative charges formed, accumulated on this side will produce a negative potential here. So the total potential will be the sum of positive V plus 1 by 4 pi epsilon 0 negative Q by R. So definitely the potential of this is at a positive potential. These negative charges are creating a negative potential at this point. So this negative potential will reduce the potential of this plate. So what is C? C will be equal to Q by V. So we have not changed Q here, but because of the presence of this negative charge, the potential of this plate is reduced by V minus 1 by 4 pi epsilon 0 Q by R. So V has reduced. So what will happen here? Since V has reduced, Q remains same, but V reduced. So this will cause an increase in C. But we have some positive charges formed on the other side. So this positive charge also has got an influence on this potential. Since they are positively charged, they will also produce positive potential here. But that positive potential will be slightly less than the negative potential produced by the negative charges. The reason is, I will tell you once again, the negative charges will produce a negative potential here. That negative potential will decrease the potential of this plate. But at the same time, the positive charges accumulated here will try to increase the potential. But who has more influence on this charge? Definitely the negative charge. The reason is negative charge is very close to this plate or closer to this plate than these positive charges. So negative charges will decrease the potential by a large quantity, but positive charges will increase it again. So there will be a very, very slight difference in the potential. So capacitance of this one will increase by a small quantity. Now, how can we increase the capacitance by a large amount? Who is decreasing the potential? This negative charge. Who is increasing it? This positive charge. So what we have to do? These charges are decreasing the potential of this plate. Actually, what we need that we have to decrease the potential, but at the same time, these positive charges are increasing the potential of this plate. So I want a large increase. So what I have to do? I have to remove these positive charges from here. Somehow I have to remove the positive charges. We know a technique to remove the positive charge. What do we have to do? Connect an earth wire. Connect one wire here and connect the other into the earth. We learned that earth is an electron band. So electrons will come from the earth and neutralize all these positive charges. Again, remove this one. So now what happened? All positive charges are neutralized. And now the potential of this plate will decrease by a large quantity because of the presence of this negative charge. And this will increase the ability to store more charges. And now this device is called a capacitor. We will call this device as a capacitor. Since we have used two metallic plates which are parallel to each other, this type of capacitors are called parallel plate capacitors. So this is how we make a parallel plate capacitor. And now we have to derive the expression for the capacitance of a parallel plate capacitor. I think our time is almost finished. Am I right? Is the class up to 4 o'clock or 4:30? Hello, sir.
Sir, up to 4, sir.
Okay, let me continue with this. And let me
Sir, up
finish.
to 4 only, 4 only.
Okay. We will see a parallel plate capacitor also. Is the derivation required? Capacitance of a parallel plate capacitor, is it required?
Sir, time is up, sir.
Okay. The expression for the, I will tell you the expression for the capacitance of a parallel plate capacitor. So this is a parallel plate capacitor, which has got positive charges Q on this and negative charges Q. Surface density of charges are sigma. And we can find the capacitance by using the formula Q by V. And finally, it will be equal to epsilon 0 A by D. The capacitance is given by epsilon 0 A by D, where A is the area of the plates and D is the separation between the plates. So how can we increase the capacitance of a capacitor? They can either increase the area and we can decrease the distance between the two plates. So we can, let me conclude it and we will move with the, we will see with the numerical problems in the evening session. So you can also send, if you have any doubt, I will clear it in the evening session. Okay, thank you. നിർത്തി sir. നിർത്തി Pause. എന്ത് ചെയ്തോട്ടെ? Okay, you can leave the meeting and see you at 6:30 again. We will discuss some problems, especially I have selected some problems from sample purpose and previous year's question papers. We will see it.